where this expression will be then given by 1 minus 1 upon beta dabba by dabba epsilon s of ln of z. We call this as equation number 5. Okay, so this is nothing but the mean number of particle uh, for a given single particle state s. Okay, and then we have expressed this partition function like this. Now you remember that this is a distribution, so what it is going to do generally, it is going to give you, so if I have a number of particles, okay, and let me say that these are my n number of particles, and then there are r number of states, then r number of states, then I'm going to specify this probability, okay, n of r, and then but then this will be a mean probability because this will be one of the combination, this will be one of the microstates. So you remember our old discussions about these coins experiment with n string coins, so it will be similar thing. Okay, so we have this partition function written. Now how you will calculate the dispersion, calculation for dispersion? So we can write this expression for dispersion by using this thing. So delta ns bracket square bar is equal to ns minus ns mean whole square mean square is equal to square of the mean, which is nothing but if you do it you will get it ns square bar minus ns bar square. Okay, we'll call this as relation number 6. This is relation number 6, and uh, for for ns square bar we can write by definition, which is equal to summation over r ns square e raised to minus beta n1 epsilon 1 plus n2 epsilon 2 and so on and so forth divided by summation over r e raised to minus beta n1 epsilon 1 plus n2 epsilon 2 and plus so on and so forth. Okay, we will call this as relation number 7. And then when you will simplify this, so how to do it? So ns, just a minute, ns square bar is equal to 1 upon capital Z summation over minus 1 upon beta dabba epsilon s into minus 1 upon beta dabba epsilon s into e raised to minus beta raised to minus beta and to minus beta e raised to minus beta. Let me erase this. Wait a minute. Let me put it. over here only. ns square bar is equal to e raised to n1 epsilon 1 plus n2 epsilon 2, so on and so forth. Okay, which is equal to 1 upon z into minus 1 upon beta dabba by dabba epsilon r of square raised to z, which is equal to 1 upon beta square z dabba square z by dabba epsilon s square. Okay, this is s, not r. Okay. And then we'll call this as relation number 8, and then we can put it in more convenient form. Okay, and then we can have this n s square bar is equal to 1 upon beta square dabba by dabba epsilon s into 1 upon z dabba by dabba z by dabba epsilon s plus 1 upon z square dabba z by dabba epsilon s whole bracket square, which is equal to 1 upon beta square dabba by dabba epsilon s into dabba ln z by dabba epsilon s plus beta square ns square, which is equal to using our equation 6, this equation will now become delta ns square bar is equal to 1 upon beta square dabba square ln of z by dabba epsilon s bracket square. We call this as relation number 9. By using 5, we'll get delta n s whole bracket square mean or bar is equal to minus 1 upon beta dabba ns bar by dabba epsilon of s. We call this as relation number 10. So calculation of all this physical quantity of our interest, okay, this shows simply the evaluation of the partition function, which is given in equation number 3. So this is what we are evaluating indirectly. Okay, and now to vary the the mean. Okay, especially from, so once we have this thing in place, we can in Maxwell-Boltzmann distribution how this thing is going to work. So here we have to sum over all particle numbers of in each state, and this is for all over state, because there is no such thing, because particle are perfectly and since this is a classical distribution, this we are going to distinguish the particles. So in case of Maxwell-Boltzmann distribution, our nr will be given by simply 0 1 2 3, so on and so forth for each r. And what is our r by our notation? Our r is nothing but it's a possible quantum state for a single particle. But this distribution is not quantum mechanical, so it is going to perfectly obey the classical distribution. Now let us see. Now if we look at equation 2, okay, for the fixed total number of particle, that is, I am looking for r number of particle. Okay, so now since we have distinguishable particle, any permutation. So for example, I have these two particles which are distinguishable now. One is like this, another is like this. Okay, So any permutation of two particle in different state must be counted as a totally different state. So if I have this thing, and then if I have this thing, this is my new state. Okay, this is my new state. So and so then how many states will be there? There will be, in fact, there will be probable states will be n1, n2, n3. Okay, so on and so forth, nr. Okay, so whereas in case of now you, if you look at same thing for Bose-Einstein statistics, you look it from the Bose-Einstein statistics. In Bose-Einstein statistics, particles are indistinguishable. So we have indistinguishable particles. We have indistinguishable particles, and then once you have indistinguishable particles, now if I have indistinguishable particles, what is going to happen? As we see yesterday, there will be combination of the states. There will be combination of the states. Okay, and then in that case, okay, in that case, what is going to happen? In that case, I will have still validity of this relation. Okay, I'll have still validity of this relation. I can still count my states, okay, to be 0, 1, 2, and so on and so forth. But in case of Fermi-Dirac statistics, what is going to happen? In case of Fermi-Dirac statistics, what we have seen last time, that we will not have any combination, not have any combination. So in that case, we'll have only two states. We'll have only two possible combination. One, why? Because one will be up and down, cancelling to 0. One will be up and up, contributing to 1. So that be uh, this is the thing which is very important in setting up the states, distinguishable states, which we are looking for the, or number of states which we are counting for three statistics: Bose-Einstein statistics, Maxwell-Boltzmann, Bose-Einstein, and Fermi-Dirac statistics. Okay, Fermi-Dirac statistics. Now, but now there are two things which we have to look into. There are two things which we are going to look into. First is we have to have this partition function to be look from the symmetric calculation. So we have to see, because if you remember that our Bose-Einstein distribution, Bose-Einstein distribution is symmetric distribution. Okay? It obeys the symmetry. Whereas if you see Fermi-Dirac distribution, it is anti-symmetric. It is so whenever you will be setting a partition function, okay, in a specific for a specific ensemble of particles, okay, you have to take into consideration of this thing. Now for example, now if you want to have same thing, okay, so for example, if I have same thing applied to a photon gas, for the of this case, that the total number of particles are not specified. Okay, total number of particles are not specified. So still, we will have our mean particle distribution be given by like this: summation over ns e raised to minus beta ns epsilon s, okay, divided by summation over e raised to minus beta ns epsilon s. This is the thing which we are going to get for a photon gas even. But now when you will calculate it, okay, when so rest of the calculations as straightforward as we have seen, but I'll reproduce certain thing. Ns will be given by then minus 1 upon beta da by epsilon s of summation raised to divided by summation e raised to minus beta ns epsilon. You see our partition function which previously, okay, or this thing, and now over here they will be they are going to be, and they are going to be having a slight variation. They are going to have a that one. So in this case, which is equal to minus 1 upon beta dabba by dabba epsilon s into infinite geometric. So we'll consider this as a infinite geometric series. Okay, and we can write them in summation ns is equal to 0 to infinity e raised to minus beta ns epsilon s is equal to 1 plus e raised to minus beta epsilon s plus e raised to minus 2 beta epsilon s plus e raised to minus 3 beta epsilon s, and so on and so forth, which is equal to 1 divided by 1 plus e raised to minus beta epsilon s. So this equation 2 will finally give us my ns to be equal to 1 upon beta dabba by dabba epsilon s of ln 1 minus e raised to minus beta epsilon as a function of n and e. This distribution, how this distribution will look like? This distribution will look like this. black body curve. Okay, and when you will start changing beta, okay, it will have different type of thing. आपने देखा है क्या ये ब्लैक बॉडी कर्व? हैव यू सीन दिस थिंग? आपने देखा है कि ये ब्लैक बॉडी कर्व देखा है?
Yes, sir.
Now let us do one more thing, one more calculation. Okay, let us see this FD distribution. See this Fermi-Dirac distribution also. Now for this thing we'll keep our number of particles fixed. Number of particles fixed. Just say I will fix to n. And then once we put this restriction, okay, the things will become a little bit complicated. Okay, if the relation which we have written, this relation ns thing is going to be bit modified. This relation ns bar is equal to summation over ns e raised to minus beta epsilon sns. Okay, now there will be, since we are going to restrict our particle to s state, so there will be another term which is coming over here, n1 n2 so on and so forth up to s, because we fixed it. And then e raised to minus beta n1 epsilon 1 plus n2 epsilon 2 so on and so forth. This is whole divided by summation over ns e raised to minus beta ns epsilon s to summation over n1 n2, okay, e raised to minus beta n1 epsilon 1 plus n2 epsilon 2 and so on and so forth. This will be the thing which will come into the picture. And then if we have whatever thing which you are going to fix, okay, you will have only total nr will be given by 0 and 1. Okay, will be given by 0. So this restriction will imply that if one particle is in state s, the summation over s, okay, of this above equation will extend over the remaining n minus 1 states. So if you have, so you know this thing, correct? So if s is equal to 0 and s is equal to 1, so we'll have one state over here, so then n minus 1 will be this state. So then in that case I can write my partition function for fixed number of particle, which will be summation over n1 comma n2 so on and so forth, okay, up to fixed number of particles e raised to minus beta n1 epsilon 1 plus n2 epsilon 2 so on and so forth. Call this is relation number 3. And then if n particles are to be distributed over these remaining states, okay, it's going to have only 2 states. Okay, so what is going to happen, we'll have only two terms which are going to come into the picture. So how we will write our ns? We'll write our ns bar mean ns is equal to 0 plus e raised to minus beta epsilon s into z, okay, into n minus 1 divided by z s of n plus e raised to minus beta, because we have fixed number of states, z into n minus 1. we call this as relation number 3. And then when you solve this, so let me put it in more appropriate form. It will be like 1 divided by zs of n divided by zs of n minus 1 into e raised to plus beta epsilon s plus 1. Well, this is relation number 4. And then this can be, we can simplify this by saying that uh, Zn of, because in any case you will have n number, so whatever partition function which you are going to write for n number of state will be, will have same amount or with in same proportion to n minus 1 state. So in this relation number 4, we will use this relation and then so we can write this, and then alpha s is equal to okay. Only 2. Okay, and then we will use this, we will use this relation, this thing, okay, with delta, let delta be equal to 1. And then in this relation, this alpha is determined from the condition of equation. So alpha is determined by summation over nr, okay, which is equal to n. Okay, and then or We can write, in other words, we can also write okay. So since we have summation over nr, okay, to be equal to n, we can write this, which is equal to summation over r 1 upon e raised to alpha plus beta epsilon r plus 1 is equal to n. Okay. Now we know that this free energy, F is given by minus kT ln of z. Why? Because I put as this thing, which is equal. Okay, and then we can write the final form. Ns is equal to 1 divided by just a minute. One divided by e raised to beta e raised to beta epsilon s minus mu plus 1. I call this a relation 4, 5, 6. Relation number 6. And what is this? So what is the condition of this ns? We have condition on ns to be less than 1, greater than 0. Okay. So which is exactly what is the Pauli's, which is also reflected in Pauli's exclusion principle. Okay. So this is now you can calculate, for example, if you have given this thing, then how to calculate this. Have you got this thing? समझ में आया कि ये समझ में आया क्या? Okay, so this is what is this. So this distribution is nothing but your Fermi-Dirac distribution, Fermi-Dirac distribution function with this condition on mean value of mean energy, mean occupancy is given by this thing. Okay. Shall we stop for today? Shall we stop for today?
Yes, sir.
Okay, we'll stop for today. Okay.